All right, everyone, welcome back to our third session of VMCAI'23. This afternoon we have one invited speaker followed by a regular contribution paper and one session following that after the coffee break. For now, it's my pleasure to introduce Aws from the University of Wisconsin-Madison. Looks like he has a talk that's going to have wide-reaching social implications. Take it away.
Thank you for having me. This talk will have verification, model checking, and abstract interpretation, and more. Sorry. So much of the work that I'm going to talk about today is the work of this fantastic student, Anna Meyer, who I co-advise with my colleague, Laura Stantoni, who unfortunately couldn't make it this week. But this is this is the canonical paper which we're going to cover today. There will be other stuff at the end, but that's the crux of the work. So sort of at this point in time, everyone has used machine learning, is probably working in machine learning. It's in our phones, it's in our laptops, it's everywhere. And many people are concerned about that, all the negative things that can happen. And many people have written books about it. It's become like a thing to write a book about the negative consequences of machine learning. So there are books titled, Algorithms of Oppression, Automating Inequality, Weapons of Math Destruction, Artificial Unintelligence, and many more, right? And one of the sort of the problems that people are very concerned about and has been a question of study in the literature is consequential decision making. So whenever you use machine learning or any kind of automated decision process to make decisions that affect people's lives, whether to give them a job, to give them a loan, to deny them healthcare, or decide what to do with them, promote them or not, etc. So to give you two examples from the United States, this is a study that appeared in Science a few years ago, received a lot of attention, on a specific algorithm that is used in the healthcare system, across many providers in the United States, where your data goes in and it decides whether you're a high risk or low risk, and depending on your risk, you'll get different levels of care. Like you'll only see the nurse versus you see a specialist versus you go to the ICU, etc. And it's been shown that it always, or on average, predicts lower risk for black patients. Okay? And this is run every year on hundreds of millions of people. Okay? So imagine the consequences, the deaths that could have been prevented, etc., from using a better algorithm. Another example from a few years ago. And of course, here you can question the use case itself, but there's an algorithm that's used in the court system and other pieces of the criminal justice system for risk assessment as well. Okay, so say you're convicted of a crime, and they want to decide whether to keep you in jail until the court date or to let you out on bail. Then they can use a risk assessment algorithm that decides whether you're high risk or low risk for recidivism, meaning repeating a crime. And again, it's been shown in this ProbabiltiY investigation to be, biased against black defendants. So again, as you see, many big problems. And I just want to take a second to acknowledge the sensitivity of this problem and the gravity of it, right? So whenever we talk about consequential decision making, at least in the context of the United States, we typically are concerned with minorities like African Americans. And of course, they've suffered a long history of injustice and oppression that continues to this day. And whatever I do as an academic is a very, very small contribution to the big picture. So think of this stuff as negligible, but yet, important going forward when it comes to growing impact of consequential decision making. All right. So if you think of machine learning from a caricature perspective, there's a data set D that comes in, there's a learning algorithm, and the learning algorithm learns a model. We're going to call the model f of D. Okay, so this is the model that's learned from this data set. And then you can use that model to make predictions about the world. So for simplicity, we're going to use this data set as an example. So here it's a hiring scenario. Okay? We're trying to hire people. So these people take a test, get a score, let's say from 0 to 10. And depending on that score, we're going to decide whether they're going to be hired or not hired. And this data set is historical data, how well people did on the test, and whether what is the score on the test and how well they did on the job. Okay, so I'm going to try to learn from this historical data. I mean, clearly this is a toy example, so people with high scores are, do well on the job. People with low scores don't do well on the job. And here I've divided people into two classes, black and white, but you can imagine, many other nuanced subgroups. Right? So the X's and the check marks are whether someone did well or not well on the job. So now I can take this data set, feed it into the learning algorithm, and it produces a predictive model f of d, whatever it is, could be a neural network, a decision tree, whatever it is. And then I can take this model and let's say someone new comes in with a score of 8. This may be too small for people in the back. It's even small for me. And this person gets the job because perhaps their score is high. Cool. So in the literature, people mostly have been concerned about the problem of f of d. We're going to take f of d and apply it in the wild. What's going to happen? Okay. So people try to equalize certain metrics. For example, you want to say that the selection rate, the number of people I hire, the proportion of people I hire from the white applicants and black applicant pools are similar, well, up to some epsilon difference perhaps. Maybe you try to equalize false positive rates or other important rates, metrics for the specific domain that you're dealing with. Okay? So this is all important, but it kind of misses a big chunk of this pipeline, the machine learning pipeline. Specifically, not many people think about the dataset D. Okay? So this dataset D, where did it come from? Who generated it? Does it have historical biases? Okay? For example, this is hiring data about how people did on the job in the past. It could be wrong. It could suffer from systemic biases in the past. Maybe there were sexist managers who were not promoting women. Maybe people were just felt alienated and left the job or didn't do well as a result of the environment, et cetera, et cetera. So all of that stuff is not reflected in the data. And it's really, really hard to tell, to go back to the past and kind of question the data. Right? So you have to kind of take it as it is. Right? So ideally, if you have such a problem where you don't trust the data, or the data may contain historical biases, you want to make sure that your learning algorithm is robust to that. So even if there had been or hadn't been injustice or unfairness in the data set, the outcome model should not make very different predictions. Okay? So it should be robust. It should tolerate some level of bias in the data set. Okay? So our goal today is to take a learning algorithm and prove that this learning algorithm is robust to data bias. Okay? So two keywords here are robust and data bias, and I'm going to explain them in a bit. So first of all, what do we mean by data bias? There can be many different forms. For example, historical biases in the data. One example is perhaps sexist managers giving low ratings to women. So you'll have a data set where women employees have systematically received lower ratings. Maybe some of them, not all of them. Yeah? There could be missing data. You may not have data from for example, low-income neighborhoods. Okay? So that results in some kind of bias in your learning process. You could even have fake data. So this could be like malicious actors trying to influence your learning algorithm by giving you bad data on purpose or maybe even not on purpose. You can even think of over-collection of data for certain groups as if someone has given you fake data, etc. Yeah. So the work that I'm going to describe here can address all these kinds of bias as well as combinations between them. But for the purpose of this talk, I'm going to use the first example here, which is historical biases in annotated data. Typically in the literature, people call it label flipping because you can imagine someone who should have received a positive label, stay in the job or get promoted or get a loan or whatever, received the negative label instead. So their label has been flipped. So this is what we mean by data bias. And now what do we mean by robust to data bias? Okay? So here it gets fun. Again, this is our pipeline. Dataset D comes in. There's a learning algorithm. You get a model. Okay? And the robustness here is with respect to this learning algorithm. Small shifts in the data set, some bias here, should not make the model make very different predictions. So let's formalize it. This is the most important slide in the talk. After that, it's kind of just technicalities, as they say, right? So let's imagine that our bias model says that up to n items in this data set may have the wrong label. Okay, so we don't know which n items in the data set. N here is some constant that we pick, an upper bound on the level of bias. We don't know which items, but up to n items are wrong. They receive the wrong label. Okay? And now a new person comes in, their name is X, and we want to apply F on X. But we want to assure this person that even with this model of bias over there, up to n items are wrong, your prediction will be the same. Okay? So here's the statement. So take any data set D prime that is just like D, but flip up to n labels. So take just arbitrary n labels and flip them around. Okay? And now run the learning algorithm again. The model you learn from D prime should produce the same prediction as the model you learn from D. Okay? So this is, in a sense, a form of a hyperproperty, as we say in verification. You have two runs of the algorithm, one on the actual data set that you have, and another one on hypothetical data sets that you generate. Okay? Any questions about this definition? Yeah. How big? What do you mean the models? The D. So datasets. Oh, I see. So the size of the data set could be, usually we think of n as a few percentage points of the data set. So you can have like a data set of size 1,000, maybe n is equal to 10. Okay, so we're assuming that the bias is contained. Okay, it's not like 50% of the labels are wrong, because if that's the case, then we can't say anything conclusive. Does that make sense? Any other questions? Okay. Cool. All right, so let's take our example data set that we've had, and let's assume that for this specific definition that we have here, n is equal to 1. Okay? So this means if I want to prove this bias robustness property for a specific individual, then I have to consider every version of this data set where I've flipped one label. Okay, so I take this label, flip it from negative to positive, then take this label, flip it from negative to positive, and train, in this case, I think 9 or 10 models. Okay? And then compare the results. What's the problem here? Yeah, there's a combinatorial explosion. For n equal 1, doesn't matter. But as n grows, of course, as an example, if you have d is equal to 1,000, let's say, n is equal to 10, meaning you believe up to n labels have been given, up to n points have been given the wrong label, then you're talking about 10 to the 23 data sets. Okay? So it's a combinatorial explosion. In fact, it's worse than a combinatorial explosion. For some bias models like missing data, it can be infinitely many data sets, because you don't know what you're missing, right? So people can give you anything. So what do we do? Right? So effectively, the problem that we have is we have a learning algorithm. We have a whole lot of training data sets, maybe combinatorially large space or maybe infinitely many. And we want to train the learning algorithm on all of them, okay, individually. And as a result, produce a bunch of models. And I want to make sure all these models agree on a prediction. And if I can do that, then I've proven robustness. So this seems like a very hard problem, but it's kind of bread and butter verification, model checking, and abstract interpretation. We have very large space. What do we do with it? So our idea was to actually represent this space symbolically. So the set of data sets, we're not going to explode it and look at every possible permutation. We just symbolically represent the whole thing. And then we're going to train the learning algorithm, or perhaps abstractly interpret it in some sense, on this very large set of training sets, okay? And then produce a set of models, okay, that again is symbolically represented compactly, that I can prove something about them. So that is the general idea. Okay? So we're just going to use the playbook of program analysis and abstract interpretation. So roughly speaking, we have a learning algorithm. Let's call it learn. Takes a data set, produces a model. And now what I want to construct is an abstract learning algorithm, or an abstract interpretation of a learning algorithm, or an abstract transformer, depending on where you come from. People use different names, but it's going to take a set of data sets represented symbolically, and it's going to produce a set of models also represented symbolically. And of course, it may lose precision, meaning I might get more models than I would get normally by training on all the data sets. So that's my goal, is to construct this abstract learning algorithm. All right. So specifically, I'm going to look at a specific learning algorithm, which is decision tree learning. Why decision tree learning? Decision tree learning because decision trees are interpretable models, meaning I can look at them and I can understand what they're doing. Like I can explain to a human what the model is doing, and that's something that's desirable whenever you're making consequential decisions. You don't want to say, okay, the neural network said that. Decision trees are more easily explainable. All right. So hopefully I've convinced you that this data bias robustness is a desirable problem. You don't want historical biases to creep in and affect the decisions, the consequential decisions that you're making about people's lives. What I will do next is I will show you a specification language for these bias models. So this allows me to kind of symbolically represent all these data sets. And then I'll show you how to abstractly interpret the learning algorithm on those sets of data sets represented by this simple language. So how do we do that? Like, how do we take a learning algorithm and make it run on a set of data sets? That seems like bizarre, right? Like, it seems very hard. But if you think about it, if you look at a learning algorithm, like any kind of like open any machine learning textbook and look at a learning algorithm or even a statistics textbook, what do you see? Those learning algorithms may look complicated, but ultimately they're composed of very simple operations. You compute the mean, you compute standard deviation. Even if you look at like something as crazy as stochastic gradient descent that powers all neural networks, neural network learning these days, what is it doing? It's computing a bunch of derivatives of all the points in the data set and then taking the average. That's it. Like that's all it does. Okay? So if I can interpret each of these core operations and lift it to operate over sets of data sets, then I can compose them together and construct a learning algorithm that runs over sets of data sets instead of a single data set. So to give you a very, very simple example of what I mean, so imagine the count operation. Okay? So count is an aggregate statistic, takes a data set and gives you an integer, where the integer is the number of elements in this data set. It's cardinality. And what I want to do is define an abstract version of count, okay, that takes a set of data sets, again, represented symbolically. Think of it, this is an element of an abstract domain. I will talk about that more in detail. And what it will produce is an interval of possibilities. Okay, so this is kind of like the lower bound and upper bound on the possible size of the data set. Okay? So this will be the lower bound, upper bound, something like from 10 to 15. Okay? So that's what I mean. And then you can imagine, same idea for many other operations, and I will show you many examples as we go forward. So that's the insight. Okay, so now let's think of a data set and how to abstract it, or how to represent a whole lot of possible permutations of a data set. Okay. So this is our original data set that we were playing with. Okay. I'm going to use this notation, which says flip one label in the data set D. Okay. So this notation represents all possible data sets that are just like D with up to one label flip. Okay. So I can take D itself, because the keyword here is up to. Okay, so I'm allowed not to change anything. I can take D and flip the first label, take D and flip the second label, and so on. But whenever I say flip 1D or flip 2D or flip 3D, etc., I'm not really actually exploding it. I'm not computing all those and storing them in memory. I'm just representing this symbol here in memory. Okay? And all my operations will be over this symbol. Another more nuanced bias model is to say flip one element, and then this little phi here, it's like a guard that tells me, for example, only flip negative labels of black applicants in the data set. Okay? And this allows me to talk about historical biases that are more targeted, like, for example, black employees in the past, we believe that they did not receive a positive label when they should have. And what this says, that if you see a negative label for a black person, treat it as if it's positive and kind of rerun the analysis and see what happens. So in this specific case, we have two negatively labeled black applicants in this data set. So we can just flip the first element and flip the second element, and we get three different data sets. Yes? Sorry. Uh-huh. I guess I will give examples, and then hopefully it'll make sense. But for the purpose of this slide, I hope this makes sense, right? Like, so this is a set of data sets, which I'm going to call an abstract data set. And I'm going to represent it symbolically. So this is just an illustration of what it will look like. I will never actually like explicitly enumerate things. Right. So yeah, I'm flipping those labels. Those are the labels, the prediction, the things that I want to predict. Does that answer your question? Or I think you were connecting it back to the intervals part, and I will give examples about that. Is that where the disconnect is? Okay. Cool. Yeah. All right. So let's look at the counting example, which I just talked about. So this is our original data set. And one kind of standard operation you might ask is how many positively labeled elements in this data set? So I can go 1, 2, 3, 4. Well, the answer is 4. I can count. How many negatively labeled? 1, 2, 3, 4, 5. Okay, good. 5. Cool. So now let's go to the abstract world. And here I have the set of all data sets where I'm allowed to flip one label. Okay. How many positively labeled elements are here? Well, it depends on what I flip, right? So if I flip, a negatively labeled element, I will get 5. If I flip a positively labeled element, I will get 3. So effectively, I have an interval between 3 and 5. Okay? Same thing with negatives. Okay, how many negatives? Well, it depends. I can take the 5 and make it a 6, or make it a 4. So here I will have the interval between 4 to 6. Okay? So notice what we can do here effectively is compute the count for a combinatorially large set of data sets without actually looking at them. We're really computing an upper bound and a lower bound. We're not computing explicit counts, but that's the idea. Right? And this can be easily computed. So in the normal world, imagine that we have a function that takes a data set and a label and counts the number of labels y in this data set. In the abstract world, I want to define an abstract count, or an abstract transformer for count, that takes the symbolic set of data sets, or an abstract data set, and a label, and counts the number of labels there. And I can easily define it by computing the normal count, subtracting 1, and adding 1, and coming up with an interval. And this operation easily generalizes to n greater than 1, so any arbitrary n, by simply replacing the 1 with an n and replacing the 1s here with n's. Cool. And that's pretty much the recipe now. Just take things that are more complex than count and lift them so that they can work for abstract data sets. Yes?
Is it okay to bash AI and VMCAI'?
Let's take a poll. Yeah, absolutely. Yeah.
So you made you lost information.
By AI, you mean abstract interpretation? Okay, yeah, okay.
So you made a choice, right? You lost information
Yeah,
in your abstract domain.
yeah.
Isn't that a hack?
Yeah, it's a hack. Yeah, I mean, it's a deliberate choice. There's many, many other ways to do it. Yeah, but this is kind of the...
So ideally you could say, what is the abstract domain that precisely captures the power sets?
Right, yeah. So I think for most of those operations, we have proofs that they're the tightest abstract transformers. I believe all of them are the tightest. I don't think we can go any tighter, at least for intervals. I mean, you could imagine other more complex domains, like BDDs or some.
Within the domain that you choose, but
Yeah.
they're not tied with respect to the power sets and entails.
Oh, I see. Yeah, I mean, yeah. They're not. What do you mean? Within the interval domain, they're the tightest. Yeah.
Exactly.
Yeah, yeah.
But if you want to really capture
Yes, yes, yeah, yeah. I mean, there's loss of information. Is that? Yeah, yeah, absolutely. There is loss of information. Yeah, I'm not trying to be precise. Yeah, yeah. It just for efficiency. I could try to be more precise, maybe like capture things using, I don't know, a BDD or something specific and capture all possibilities, but it gets hairy very, very quickly. So it was like it's impossible to construct proofs. I mean, even with this, it'll get hairy, and I'll tell you why in a bit. So there's a lot of hacks, right? But it's sound hacks. Yeah. Yeah.
So why? So now the key part is symbolic, but why is it still concrete?
Right. So y is concrete. Y is a label, and I'm counting the number of labels y in this set of data sets. Yeah. Yeah. For this specific algorithm, I don't need y to be. Y is typically just a positive or negative. So. All right. Okay, so another example, this is like the ratio or probability operator, pops up in many places, including decision tree learning. So maybe I have a function that says, what is the probability of drawing a positive element from this data set if I just uniformly draw? It's 4/9 because there's 4 elements positive labeled and total number of elements is 9. Now I can ask the same thing for what is the probability of drawing a positive elements from this abstract data set. And again, this abstract data set says up to 1 label is flipped. And the answer is 3/9 to 5/9. Okay? And how do you implement that? Well, in the concrete world, you count and you divide by the size of the data set. In the abstract world, you also count abstractly, and then you divide by 9. Okay? And this is what you get. And you can keep going. All right, so let's talk about decision tree learning, which is the algorithm that we want to abstractly interpret. I showed you examples of things that are performed within decision tree learning, but not the whole thing. So now I'm going to walk you through an example of decision tree learning abstractly performed. All right, so first, I'll just do a normal pass of decision tree learning in case you've never seen it before. It's a very simple algorithm. And I'm going to learn a decision tree of size 1. Okay? So a decision tree of size 1 is really just one predicate that says, if your score is bigger than blah, then you get the job. If it's smaller than blah, then you don't get the job. Okay? So the first operation in decision tree learning is finding a predicate that with the lowest entropy. It means that lowest entropy just means the cleanest cut of the data set. As you can see here, the cleanest cut should be around here. Okay? So let's assume that it's x is less than or equal to 3 will be the best predicate here. Okay? So you'll get a decision tree like this. Okay? And then the next step is you split the data set into 2 pieces, those that satisfy the predicate and those that don't satisfy the predicate. So those are the ones that satisfy the predicate. Whoops. Look at that. All right. And this subset of the data set, I'm going to call it D underscore less than or equal to 3. Okay? So this is the subset that have score less than or equal to 3. And then this other subset over here is D greater than 3. Okay? And then finally, sometimes you can keep going and build a larger tree, but I'm going to stop here and just end the algorithm. So what I do at this point, I look at each of the branches and I compute classification probabilities. They're not probability in any kind of statistical sense. It's just like a ratio. So what is the ratio of negative to positive out of this data set? It's really like, the probability is 1. So this is the dominant class on this side. So essentially, if you end up on this side of the tree, you don't get the job because that's the dominant class. Here, the dominant class is positive because its probability is 4/5, meaning it's greater than half. So if you end up on this side, you get the job. Okay? So now I have a tree that looks like this. So let's say someone comes in, their score is 9. We ask, how is the score less than or equal to 3 or greater than 3? It is greater than 3, so they go over here, and they get the job. So that's normal decision tree learning. But now, this person will ask me, what happens if there was bias in your training data? And I want to kind of assure them that even if there was bias, you will still end up on this side of the tree. So we'll now talk about abstract tree learning. So this is the concrete algorithm, and now I will think of its abstract version over here. So each of these operations is going to be lifted to work in the abstract world. Okay, so instead of a data set D, I will have an abstract data set. For simplicity, I'm going to assume this bias model, okay, where we're only flipping the labels of negatively labeled black applicants in the data set up to one person. It's a small data set, so one person is here, it's 10% or more. Yeah. So instead of finding a single predicate that splits the data set cleanly, I need to find a set of predicates, right? Not a single predicate, because now we're dealing with a set of data sets. Okay? So there's not a single nice split in the middle. Yeah, there could be many possible splits. Yeah? So it's kind of like a power set domain of some sort. All right. And then I'm going to split this abstract data set. I'm not splitting a single data set. I'm splitting an abstract data set in two. Okay? Pretty cool. And then I'm not computing a single probability, a belief. I'm computing a range of possible probabilities, an interval of probabilities. So that's the abstract version of this. Essentially, take any operation. Instead of spitting out a single result, it spits out a set of results. And this will end up giving me a set of decision trees, or an infinitely many decision trees, depending on how you see it. Okay. So let's walk through this example. I'm starting with this abstract data set, where up to one label is flipped, meaning this label is flipped or that label is flipped. It's a small one. Okay. And the first thing I'm going to do is I'm going to find the predicates with the lowest entropy. Okay. In this specific example, it turns out that this is the only predicate. I'm not going to go through the how we do it. It's a bit complicated, but trust me that this is the best label here, and there's only one. But I'm going to represent it as a set because there's a set of possibilities, just a singleton set. The next thing we'll do is we're going to split this abstract data set into two. Okay? How do you split an abstract data set? This is a set of data sets. Okay? It turns out that you actually only have to split the concrete data set. So I will split the concrete data set, just as I did before, and then abstract it again. Okay? And same thing over here. And why does this work? It works because we have a little theorem that says, if you take an abstract data set and split it, in other words, split each element in this data set, it's the same as splitting the original data set and then performing the abstraction. Okay? Why is that? Because the splitting is on features and the flipping is on labels. So they're completely two different spaces. You can commute them. Life is easy. Anyways, so now this part goes over here. And again, we abstract it again. Okay? There's a loss of precision here. Anyone see a loss of precision in this process? Subtle. So the loss of precision comes from the fact that in my abstract data set, I'm assuming that up to one label is flipped, right? And then I split that data set. So that label that was flipped either should go here or there, but I don't know where it went. So that's why I have one here and one there. Yeah? Ideally, each one of them should be 0, but I can't tell where it went because I don't know where it is. So I'll make a worst case assumption that it's in both places.
What if that is not 1, it's 5, for example? How do you both of them get 5?
What do you mean by the 5?
Right now it's flip 1.
Oh, I see.
What about
Yeah, they'll both get 5. Right. I mean, you can be probably more nuanced and kind of look at the splits and see if there's anything you can do to tighten. But the official abstract transformer is this. Cool. All right, and then I compute a range of probabilities. So if I go over here, the dominant class is negative, except of course I can flip this label. So the dominant class probability is between 3/4 to 1. Over here, the dominant class is positive, but I can flip this label. So the dominant class probability is between 4 and 5 and 1. Both of these are greater than half, so it really doesn't matter. So those intervals are above 1/2. Okay. So this is my final abstract decision tree. Think of this as an infinite set of decision trees. Any decision tree that has this structure and the classification probabilities are within those intervals. Okay? So many decision trees look like this. So now let's say this person comes back again and applies for the job. Okay? Is their score greater, less than 3? No, it's not. So they go over here. They get the job, and they get the assurance that even if there had been bias against black applicants in the past, up to 1 label flip or 10% roughly of the data set, then your classification would not have changed. So you get a classification, you get a proof of robustness. And that is the idea. Yeah.
So I think all your other transformers were parametric in the data sets. This one is not. It's specific to one data set that you created the decision tree x less than or equal to 3. So for a different data set, it could be different.
Which transformer are you asking about? Because you said this transformer. Which one are you referring to?
You had the abstract. Previously, nothing depended on a specific data set.
I think it all depended on a specific data set, because if I'm counting, I'm looking at the original D. What do you mean?
Oh, okay. The transformer that says in the vicinity of different Hamming distance 1.
Oh, I see. You mean
it's defined across data sets.
Right, but I'm always. I'm like, for the purpose of analysis, I have a specific training data that I started with, and I'm saying anything in its vicinity will produce the same answer. Does that make sense? I'm not making a global statement about the robustness of the algorithm. I'm making a local statement about the robustness. Yeah. Is that the question?
That's the answer.
Okay. All right. Cool. Thank you. A great question. Yeah. That's good.
From what I got, it looks like that once you abstract, the result is robust, mainly because of the first step, where the predicate with lowest entropy, even in the abstract version, is a singleton.
Mm-hmm. Yeah.
What happens if it's not a singleton?
If it's not a singleton set, then you have to try both of them.
And it will still work, anyway. As in, it will still be robust. Because to me, it looked like, it works. The algorithm works anyway.
Yeah.
So it still gives you the same answer as before.
Yeah.
Mainly because you only had one case to look at.
Right.
And
But
it was the exact same case as before.
Yeah, there could be many. This is a very simple example,
Yes.
but in general, our implementation will have many such predicates.
Mm.
And when we want to prove robustness for a specific point, you have to try all of them. And I'm not going to go through that in detail, but you get into path sensitivity and path insensitivity problems over there. And I'll just briefly talk about it in a bit. Yeah.
Okay.
So when you're saying,
Yeah.
so when you're saying that 9, the decision made on the input
Yeah.
9
Yeah.
is not biased.
Uh-huh.
Are you looking at the probability interval that the 4 out of 5?
That's right. So if this probability interval were overlapped with 1/2, I won't be able to say anything.
Only when it's not overlapping with 1/2.
Right. Yeah. It has to be greater than 1/2.
And why is that?
Because
Why
if
is
it
1/2?
overlapped with 1/2, then I won't know what their label is. It means that there is a data set. There is possibly a data set, because we're losing precision, where you will get a different label. Okay. So exists a different universe. But in this case, it turned out fine. Okay. Yeah. Yeah.
In case of multiple predicates, how do you make the final decision?
Oh, so essentially, you have to try every possible path that you can go through. And in this case, it's a small tree, so there'll be either left or right. So you try both paths. But then imagine a bigger tree. Then it becomes like an exponential explosion of different paths that you have to consider. You can either do a path insensitive analysis where you merge the intervals, the classification probabilities. That loses a lot of precision. Or you can just explode and try everything. And that's what we end up doing. And it works out fine. For trees of depth 2 to 3 that achieve classification probabilities that are decent compared to complex models.
Thank you.
And there's another question over there.
So in case of multiple predicates,
Yeah.
is it the case that you want to make sure that for any of them, you have a decision tree where there is no interval overlapping with 1/2, or you want to find at least one predicate for you which you can construct such a decision tree, and you can just say that predicate is the one that you should use? Always.
For all, yeah. You
For
have
all of them.
to for all show that the intervals don't overlap with 1/2. Yeah.
And is the computation of the entropy also symbolic somehow?
Yeah,
in
so the
order to
entropy is a number, right?
Yeah.
And it'll be just an interval. Yeah. Right. Yeah. Cool. Okay. Fantastic questions, by the way. All right. So kind of to summarize this piece here is we're learning an abstract decision tree or an infinite set of decision trees symbolically. The abstraction, of course, as we all figured out, is sound but incomplete. As many of you have also figured out, there are many paths that the abstract tree can an input can take because there could be many predicates. So this creates a problem. You can choose a path-insensitive analysis or a path-sensitive analysis. In practice, we found that the path-insensitive lose a lot of precision, doesn't give you anything or anything interesting most of the time. The path-sensitive may blow up, but it works decently well in practice. All right, so let me show you some numbers of experiments that we've performed. So we took popular data sets from the fairness literature. So typically these data sets are data sets where consequential decisions are being made. Like you're looking at people's drug consumption habits, trying to predict their drug consumption habits. The Compass data set is what was used for that recidivism problem in the criminal justice system. It's a very problematic data set, but we're just using it here for illustration. Adult income tried to predict one's salary, like how much to pay them perhaps. And here in this specific table, we're looking at the missing data bias. So I'm saying some data is missing up to some level. Okay? And this is the bias amount. So this is the n number that I've treated before as a constant, as a cardinal, but here we're treating it as a percentage of the data set. So up to 1% of the data set is biased, or 0.4%, or something like that. Okay. And I'm trying to see how many predictions I make are robust for various levels of bias. So here we're looking at the test data, and we're saying, how many of the predictions that I make will not change with that level of bias. And as naturally, for small levels of bias, like 0.05%, that's most of these numbers are 100%. Like you can tolerate that amount of bias, and as you start increasing, then we can prove less and less. Okay? So, for instance, here for the adult income data set, which is a very popular data set that people have looked at, at 1% bias, we can prove 73% of the data points robust to that level of bias. Here you see Compass and adult income targeted. Targeted means here the missing data is for a specific subgroup. For adult income, this subgroup is women who typically at least in this data set, their salaries are lower. Cool. So here, when we talk about data, like the size of the abstract data set, like if you look at drug consumption, it's like up to 10 to the 100. For adult income, it's infinite because it's a real value data set, and we're talking about missing data, so someone can give you any real value that they want. Yeah.
How is it that the accuracy stays the same for the first subject here, the drug consumption?
Yeah, it's fine that it stays the same. It just means how many can we prove. So it just means that at 0.05 and 0.1, the robustness is we can tolerate up to 0.1. Like 94.5% of the test data can tolerate up to 0.1%. And it turns out between those, in this interval, no proofs fall out. Cool. So those are two different other bias models. This is the label flipping model that I've talked about throughout the talk. You can even compose bias models. So I can say, some data is missing and some data probably got the wrong labels, and I could compose them together in various ways. One thing you'll notice here is that the flipping model has lower numbers, right? So you can see here, for example, at 1% of missing data, 71.5. Here it's 39.7. What's going on? Okay. Does anyone have a guess? What's going on? Why is this number smaller? All right, so the reason is that flipping a label, it's as if you changed two elements in the data set. Okay? Because you removed that element and you added a new one. Okay? So it's when you talk about 1% for label flipping, it's as if you're talking about 2%. It's subtle, but interesting. All right, so we even did it for like MNIST. People always look at MNIST, and you could achieve. This is a subset of MNIST that people look at in this literature. You can achieve quite a bit of robustness, and again, with MNIST, you're talking about incredibly large spaces. All right. Another thing we've looked at, and Anna Meyer, the student, has been very interested in, is the certification disparity, meaning different subgroups will have different robustness when it comes to prediction. Yeah. So we looked at the COMPASS data set, okay? And we looked at the label flipping bias model. And we kept increasing the level of bias and seeing how many points we can certify to be robust. And naturally, when you keep increasing the level of bias, at some point, you'll go all the way down to 0. But we looked at the certification, the percentage of points we can prove robust with respect to different subgroups, like white men, white women, black men, black women. Okay? And one thing we noticed is that if you look over here, for black men and black women at 0.4%, the robustness tanks all the way to 0. Okay? So we're like, oh, what's happening? It could be, of course, just the incompleteness of the abstract interpretation for some reason happening at that point for this particular subgroup. We don't know. But then upon further inspection, what we noticed is that if you just look at black and men and women, they typically lie at very close to the decision boundary. So their predictions are not very robust. Okay? This could be just because there are fewer in the data set, or maybe it's harder to learn a good decision boundary for this group. But as a result, their decision process is very not robust for those subgroups. Okay? So it's an interesting problem that many people have not looked at when it comes to fairness of learning. So if you're interested in this kind of stuff, you can look at Anna's Europe's 2021 paper. Some of the original math showed up in the PLDI 2020 paper that will also appear, we're told, next month in CSEM. But of course, there are other proof techniques in the literature from other groups with the more kind of machine learning type of work. So in the next 5 minutes, I will talk about some other work that we've been doing roughly in this space. Okay. So what I've shown you so far is taking a machine learning algorithm, specifically decision tree learning, and asking, is it robust or not? Okay. Now we can ask a different question, which is, give me an arbitrary learning algorithm. Can I robustify it? Or can I construct a new algorithm that by definition or by construction gives me guarantees on robustness? Okay. So this piece of the talk is going to be hand wavy. So don't ask questions. So this is the expert, Yuhao Zhang, has been working on it. This is a recent paper he presented a couple of weeks ago. It's called bag flip, and you'll see why it's called bag flip. Here, the paper is about poisoning. You'll see this terminology in the literature. Poisoning means that some malicious people made a mess in your data set. Maybe gave you bad data to fool you, or maybe you just went looking like many people, for example, with code. They just go on GitHub and just grab a bunch of code. That code could be problematic, make you learn weird things, etc. So imagine that you have a training data set, and someone gives you a learning algorithm. It could be anything. It could be decision tree learning, could be stochastic gradient descent, could be anything. One idea in machine learning is called ensemble learning, meaning instead of training a single model, you train a bunch. Okay? So you start with your training data, and you sample a little bit of here. You put it in this bucket or this bag. You sample a little bit, you put it in this bag, sample a little bit, put it in this bag, sample a little bit, put it in this bag. And then you train a bunch of different models, okay, an ensemble. And then you just take a majority vote at the end. Okay? It's kind of like a committee, Each person in the committee makes a vote, and then you decide whether to hire a person or not to hire them. So this is a standard technique in machine learning. But it turns out that it gives you robustness guarantees almost for free. And the reason is, if you're only sampling, or if you're only seeing a small piece of the training data, each of these learners is only seeing a small part of the world, most of them will not see the bad data or the biased data. So maybe this is the biased data, the stuff in red. And if it's a small percentage of the large training data, each of these learners will likely not see it. Okay? So maybe only the fourth one will see it over here. Okay? So as a result, we can make a probabilistic argument, okay, for how many of these learners are affected by the bias. Okay? And the hope is that that's a very small amount. Okay? And then we can discount effectively their votes from the majority vote. So that's the general idea, is that most learners will see good data if you're doing this ensemble technique. And robustness, meaning like the N in the first part of the talk, is going to be particularly a function of majority vote. Okay? So the higher the majority vote, the more robust you are. The smaller the majority vote, closer it is to the boundary, the less robust you are. Because anyone whose decision is tarnished by biased data will probably have flipped their decision and changed the vote. Okay? So you can construct a function that you can compute analytically every time, and you get a size of robustness that you're tolerant to. So in Yuhao's case, in his paper, he looks at a specific trick where not only he's sampling from the original training data, he's also adding noise to it, and that allows him to make more nuanced probabilistic argument. You can read the paper for more detail. All right. So the pros of this approach is that we get robustness by construction. There's no abstract interpretation needed. You can just compute things analytically and return a proof. It's a probabilistic proof, but very high probability proof. So it doesn't really matter. It can work for arbitrarily learning algorithm. It's not only like decision tree learning, and it's more scalable, right? So I don't have to I don't have to restrict myself to small decision trees or anything like that. Okay? The problem, of course, is lack of interpretability, meaning I'm not learning here a single decision tree. I have just perhaps a forest of decision trees, and it's really hard to explain what a forest is doing. Each of them is different, and each of them is making a different vote. Hard to explain to a human why a specific decision was made or not made. So those are the two papers I covered, and this is kind of the big picture problem that I've focused on is what if the data is biased, and how can we prove robustness of a learning algorithm? And this will be it for today.
Question.
So for the second paper,
Yeah.
You said there is no formal proof or anything, but
Which no, there's a proof.
There's
what
a
do you mean?
proof. There's
No, it's just like when we don't have to do traditional verification.
Yeah.
It's all black box.
right.
Yeah.
Has nothing to do with abstract interpretation.
Right. That's what I meant.
Yeah.
Like there's no
That's fine.
mechanical proof that we have to construct.
Right. But I guess the I guess the performance has something to do with the size of the bag, right?
Yeah. So the size of the bag, you have two things. Like if the smaller the bag is, then it's less likely that anyone will see the poison data or the bias data, or whatever you want to call it. But then each learner will have very, very poor accuracy because they're only seeing a small part. So you have this trade-off. That's right. Yeah.
So yes, thank you for the very nice talk. So
Thank you.
my question is that I still do not understand what you mean by entropy. So when you say you minimize the entropy, you say you answered earlier that it's a number or an interval, but it doesn't.
Yeah, I mean, a simple way of thinking of entropy is if you have a set, how different are the elements? So when all the elements are the same, like they all have the same label, or they're all positive or all negative, the entropy is 0. And as you go to, if they're half-half, 50-50, the entropy is 1. And then you can extrapolate in the middle.
Okay.
Yeah.
I think it's related to the previous question, and maybe it's really more about learning. But is it? I mean, the learning problem, is not really compositional in that way. You already said something about it. That when you decompose somehow, you take bags, you sample, and you learn based on small sets. I mean, so I understand the robustness perspective, but what does it do to the accuracy of the algorithm? I mean, can you assume that you can learn in this way and then just do majority?
Yeah, so I mean, if you look at kind of, at least for tabular data, the traditional, the standard algorithms that people use in practice are of this form. You know, like instead of learning a single decision tree, you're learning a decision forest, roughly speaking. So this is the standard way. Now, I mean, in this paper, we did it for neural networks, but that's kind of like a crazy thing to do, just because training a single neural network is typically expensive. If you want to train 1,000 of them, it takes a lot of money. But, there's people at Microsoft who, are very generous, and they give money to academics and stuff like that. So.
Pardon my ignorance. I don't know a lot about the spectrum between decision trees and neural networks, but have you thought much about the kinds of limitations of the abstract domains you're using and how far they extend along the spectrum?
Yeah, there's a big gulf between the two. If you think of neural networks, you don't have to think of neural networks. You think of it as general unconstrained optimization problems. You have a quantity, you have a maximization objective, and then if you want to apply the same approach, you have to simply, abstractly interpret every operator in this optimization objective, like you have to interpret plus and minus and so on. The challenge is that if you want to apply the same approach, the abstract interpretation, is that solving this optimization objective is a stochastic process. So you need an abstract, you need a probabilistic abstract interpretation if you want to do anything like that, which is why we ended up doing a black box approach, because we didn't want to deal with probability. It's very hard to track. And then even if there was no probability, you do kind of basic unconstrained optimization using what people call a kind of traditional gradient descent. We ended up losing a lot of precision that we couldn't make any good claims. Yeah.
And are there intermediate points in the spectrum? I mean, you mentioned big gulf between decision trees and neural networks, but I would imagine that there's maybe space in between to explore, or?
Not really. But I mean, there is. I mean, and we have a paper out on arXiv on linear regression, and for linear regression, you can get a sound and complete procedure, so you don't have to lose any precision, and you can easily compute it. So it's not expensive. But linear regression is kind of the simplest machine learning. It's simpler than decision trees, at least from an algorithmic perspective. Yeah.
Other questions?
Cool. Thank you.